Okay.
Yeah.
All right, so I'll go ahead and get started. So what I'm going to do is I'm going to try to cram in two 50-minute presentations into one 12-minute slot today. We'll see how it goes. So I'm going to talk to you about two things. The first is some current work that we're doing on location-based secure encryption. And this is some technology that I've been developing with some colleagues that is actually ready for licensing. And then I'm going to tell you a little bit about my current research area, which is multi-antenna wireless communications, and some of the advances that are going on there by myself and other UT researchers. So the first thing is, I'll talk about location-based secure encryption. So let's think a little bit about, what did we used to do in the non-electronic age when you had a document or a piece of information that you wanted to keep secure? Well, the natural solution was you put it somewhere that's secure. You lock it up in a box, you put that in a room that people don't have access to, you put that in a building that has restricted access. So there's a notion of, in this case here, location and security here, because if you can't get into the place where the data is stored, your document, then you can't be viewing it. And so this is what security was in the non-electronic age. So now let's jump ahead a few years and think about electronic systems. Now in electronic systems, particularly like the internet or intranets in companies, the security cryptography is basically identity-based. So you have this set of information that maybe only a few people are allowed to view it. And you don't actually care where the information is stored. It could be stored on a server, on someone's hard drive, on a disk. But whether you can read it or not depends on if you have the correct key or code in order to decrypt the data. Now the problem with this is that while you may actually not want to care about where the data itself is being stored, you may actually care about where people are viewing the data, because you can correlate, if someone's at home and they shouldn't be looking at this data there, we want to prevent them from having access to it. So now on to location-based secure encryption. So the key features of this system are that we have some sort of encryption software, and we have a location technology. So this is something that gives us a location, and that location parameter depends on the kind of technology you're using. If it's GPS, it could be latitude, longitude coordinates, but it could be something else. So we have, at the intended device, there's some location sensing technology that provides a parameter. When you encrypt the data, you encrypt it with respect to that set of locations that is allowed for viewing that data. And so what you're doing here is we're now bringing in the notion of physical location into the whole security paradigm. And this is an interesting, flexible concept that works with other encryption technologies. So this is not necessarily a new concept, but what we have done here at UT is we've focused in on a couple of the key features that are necessary to make this system work. Now, one of them is the flexible means of deriving location. Now, kind of conventional thinking that has looked at this problem has focused just on GPS and the coordinates that we get from this constellation of satellites. Well, in fact, we don't need to restrict ourselves to this technology, and it can even be bad if we restrict ourselves to this technology, because it's known that GPS doesn't work very well indoors. So if you're in a large office building, you're in 3-4 rooms deep, you can't see the satellites, so you can't get the necessary location parameter that lets you view the data. So there, we can imagine other kinds of concepts. For example, you could deploy in the location of interest location broadcasting transmitters that broadcast information saying, if you can hear this, you can decode the data, for example. And so that's something that you could have inside. And the idea here is that this is actually very flexible, so we're not relying specifically on the coordinates of the GPS unit. We're relying on some notion of location. Now the second thing is this idea of location region. So for example, in this room here, we know that if I am allowed to view a particular document, it really doesn't matter whether I'm viewing it here or I'm viewing it over here. All of these locations should actually fall in one acceptable region. So we need to define some notion of quantization here. So quantization means, we need to be able to say that, okay, this region in this room is acceptable. So anywhere in here maps to the appropriate parameter that lets me decipher the data. Whereas if I'm outside the room, then it maps to a different parameter that doesn't let me decipher the data. And this is actually the biggest challenge in, I believe, this actually coming up with location-based technologies that are going to work is in this notion of quantization, the quantization table, and keeping that information itself secure. Okay, so just to summarize this first part of my talk, so I just talked a little bit about some technology where we're going to start taking location, embedding it into the cryptography algorithms. And some of the applications here, basically, it depends really on the market, but there's a couple of things here. One of these is e-books or DVD players. Now, take DVD players, for example. DVDs are encoded based on regions defined as geographic areas. If you have a DVD player that is capable of sensing the geographic region that it is in right now, then you can have a universal player that works anywhere in the world. It just senses, hey, I'm in North America now, so I can view these kinds of DVDs. Now I'm in Europe, I can view these kinds of DVDs. And so all of that's enabled by having this location-based technology. And as well, you can think of corporations and hospitals where you have information that, for various privacy concerns, shouldn't be leaking outside of the boundaries of the hospital. So even though that information itself, doctors, et cetera, may be allowed to have it on their laptop, when they're not in the correct facilities, they can't view the data. That's another potential application. And so we have some intellectual property filed on this topic, and you can see the Office of Technology and Licensing for details. Okay, so on to the second topic. This is vaguely related. This is on wireless communications. And so what I'm going to talk about is systems where we have multiple antennas at the transmitter and multiple antennas at the receiver. And this is a so-called MIMO communication system, multi-input, multi-output. And here's what one of them might look like. You got your base station here with multiple antennas, and in fact, most base stations now have multiple antennas. The new feature is that we have multiple antennas here at the handset as well. And it turns out that this gives us a whole bunch of interesting properties that we can now exploit. Now, you might be thinking that, this is pretty far off in the future, but I'm not sure the benefit of this to the people viewing it on the web, but I actually have a prototype here of a dual antenna phone. This is something that there's a nice form factor. I really like this, the StarTech myself. It doesn't actually work. I glued the second antenna on the back just for demo purposes. But that's where you all come in and the partnering. So this is actually the vision, though, is having one, instead of one antenna, we have 2 or 4 antennas on the handset. Okay, so here's the key features of this technology. This is the why should you bother even thinking about it. Well, we got two properties. The first one is that we can multiply the data rate. What this means is that in the same amount of bandwidth that you have, with the same amount of transmit power, total power, you can get 2, 3, 4, 10 times the amount of data on that link. And this is the only technology that lets you do that in wireless. So what this is doing is the presence of multiple transmit and receive antennas actually creates a channel that has a fundamentally larger capacity. So this gives you higher data rate that you can use to get higher throughput. You can provide users with larger data pipes. You can divide that data up into multiple users to have more users in your system. So you have more customers or customers that are paying for higher data rates. Now here's the second thing that you can do with the technology. And this is that we all have the experience of using a wireless phone and your call gets dropped because of fading. Well, we can use the multiple transmit, multiple receive antennas. There's a lot of paths between the transmitter and receiver. That's the concept called diversity. So here might be a standard signal trace over time. This is the signal level. And these dips here, these are the fades. Now what you can do with this MIMO technology, and this here is an example with 2 transmit, 2 receive antennas, you get a signal that looks like this. So you reduce the fading, you reduce the variance of the fading, and you've also increased the mean signal level. So what both of these things do is they make your wireless link look like a wireline link. So the things that you're doing for wireline, like say IP transmission, are going to work better on the wireless link with this technology. Also, you get a better user experience. We've all had that experience where you click a web page, nothing happens, you start clicking again. Well, that's pretty bad in wireless system because the wireless link can lose your requests. But if you're using this technology here, it looks more like a wire, and so it behaves more like you'd expect. Okay, so the barriers to adoption are 3 here. The first is that RF chains are expensive. So the RF chains on the phone here actually typically at least 50% of the cost of the phone. So we better be getting something out of this before we start proposing that we should add more expensive analog components to the phone. Second thing is the spacing. We can't add as many antennas as we want due to physics and physical constraints. And the third is processing, because all of these advantages actually don't come for free, which is, of course, a shock, that the complexity increases dramatically. And this requires developing low complexity algorithms. Okay. All right, so I'm going to go through now and talk a little bit about some of the work that we're doing at UT. Now, here's the, here's what we're at now. Here's my example here. Here's where, we actually don't want to be. This is kind of the porcupine phone. You can see that if you put this up to your ear, you're going to be poking yourself in all kinds of different directions. So clearly, if we buy into the concept that having more antennas is going to give us this higher capacity, higher quality, but yet we want to have small devices, we have to figure out a way to put the antennas in a seamless fashion onto the device. And this is a complicated problem because it requires, fundamental electromagnetics that's governing the coupling between the antennas, as well as understanding the signal processing issues. So we have some collaborative work along these lines. And we've constructed one handset prototypes, and this is with a tripole antenna here. So we've actually built this prototype, we modeled it, we've made measurements, and found that actually it works quite well. There's an interesting effect here of polarization and pattern diversity that existing phones and other solutions for multi-array handsets haven't found. Let's go ahead to the next one. Actually, go back one more. Okay, so I'm just going to wrap up here and talk about a couple of the other research efforts. One, we're looking at low-complexity algorithms. So we've come up with algorithms that give us near-optimum performance and yet have a very flexible, scalable trade-off. So if you say, well, this is how many gates I have on my FPGA, I can say, well, okay, here's the performance that you can get with these algorithms. So we have a family of algorithms that will do that. And we're also actively looking at this problem of increasing voice capacity. Because in 3G, this multiple antenna phone is going to be an option. It's not going to be mandatory, but it's going to be an option for both wideband CDMA and CDMA 2000. But it's only for the data. But it turns out that we can use these antennas to get 2, 3, or 4 times the number of users. And since no one's making any money off a data service right now in cellular, that's profit right there. And we're taking advantage of antennas that are already going to be there. And so finally, one of the natural applications of this technology is high-speed video, because everyone's thinking, we want to have these phones with the video technology. Okay, whether that's going to happen or not, that's another story. But it's something that people like to talk about, multimedia. Well, we have this technology that provides you with high data rate pipe, and you have an application that requires a high data rate. So it's a natural marriage of the two, and so we're currently putting together source coders and channel coders that can properly combine the features of the video application and the MIMO technology at the physical layer. So there's some great results there. Okay, so just to summarize here, this MIMO technology provides higher data rates, higher quality, more users, all of these things which can get you money in the existing spectrum with the existing power budget that you have. We have applications to cellular, wireless LAN, fixed wireless. These are all places that people have started looking at the technology. And at UT, what we're doing is we're actually attacking the key practical problems that need to be solved to make this technology happen. You can find out some more details there on my webpage, and we'll wrap up.
Yeah, a technical type question. Your problem with multiple antennas, it seems to me, might get solved with some advances in nanotech or materials where you can embed metal or electronic circuits in plastics, etc., at a very small level. Yeah,
the issues with small antennas is very interesting, and it actually requires re-examining some of the conventional techniques for antenna designs. One of my collaborators is very interested in developing small antennas that are fractions of a wavelength. So it's not so much that we can't get the antennas on the phone, it's the mutual coupling, it's the electromagnetic interaction between the antennas. That's really the problem. And so that's exactly what we're looking at right now. But if you have a way of embedding more antennas in your phone, like one way to do it is actually put a patch antenna back here. That would give us 4 antennas on this phone instead of 2. We could put another up here. So if we could do that, that would be a big. The problem is that there's some physics that tell us at some point the coupling is getting too great, so we don't get any more advantages from it. And it has to do with how close you can put antennas together, and usually it's on the order of a fraction of a wavelength, maybe a tenth or so.
Got semiconductor people here, optical lithography, etc. At Semitech. What kind of partnerships could you form with them to get at that problem?
So I have to think about that to see what the capability is. But there's some potential there. What we want to do is we want to take our technology and we want to turn it into something that is going to end up in a product. And so we've got companies right now that are thinking, we've got to provide a multi-antenna handset phone. what are we going to do? Well, if we can give them a solution that says, look, here's a phone that has 10 antennas on it, when the best that they can do is 2, that's a big win there. So there's some potential there, but I have to think about it a little bit more. Yeah.
Doctor, I have a project designing a transponder and GPS navigational system. Would you speak briefly about your connection with GPS if you're downloading navigational information?
Okay. Are you referring to the first part of the talk, perhaps, or the second part? Okay.
I'm curious.
Okay.
When your antennas intensify the GPS reception and how.
Okay. Yeah, there's an interesting question. So one of the things that the technology that I'm talking about with multiple antennas, in fact, can be used to improve the reception of GPS signals. In fact, that's something that's been around for a long time. We've got phased arrays, we've got smart antennas, adaptive antennas, but we're actually using it in a more general fashion than that, because it turns out that when we have this MIMO system, we've got a whole bunch of signals at once that are all interfering with each other, and we can use these multiple antennas to separate the signals out. We can actually do the same thing in GPS, because you think about GPS here, you've got a bunch of satellites all broadcasting, but they all have different codes, but you can use the spatial degrees of freedom to improve the separability there. So you can get, you can potentially use a receiver with a worse noise figure that's cheaper, but you have more antennas. It depends on where the cost point is there. So there is some research to be done there, and there is definitely an improvement to having multiple antennas, multiple transponders, if you will.
Other questions? Thank you. And if you have additional questions at the conclusion of this presentation, what do? The inventors are here. You can talk to the inventors. You can also see the one-page briefing that is in your packet that was given to you on the technologies. They have contact information. You can talk to the chairs of the departments. You can talk to Office Technology Licensing staff. If you'd raise your hand one more time, look around you. They'll be glad to support you as well. Or you can go to texasalliance.org. In fact, if you look at this sheet right here, the schedule sheet that came with you, top left-hand side, that's, if you want to know more about the Alliance and what we do, what the schedules are, you can look at that. Now, we started this afternoon by saying that the topic here was growth by Alliance. And I think we saw that the companies that presented in the portion organized by ATC, we're looking for alliances. We're also looking for alliances in research and commercialization. And one thing I'm going to ask you, not only is to think about alliances, how can we work together, but I don't know about you, I hate criticism of me. I hate it. But I don't know any way to improve if we don't get criticism, constructive, whether it's positive or negative. And one thing you're going to find in your emails, probably tomorrow, is an evaluation form. And I would like for you to take just a few minutes to fill out that evaluation form, because one of the things, by being here, you're part of this alliance. And I'm asking you to fill that form and give us some information on, was this useful? It takes a lot of work to put this together. The faculty have been terribly cooperative. I was told you cannot get faculty to talk for 12 minutes. I timed them. They did. They went to the effort of not only doing it here, but last week we had a practice session. So there is something we're really stepping out to say, how can we form these lines? Give us some feedback. We need some feedback. Is this useful? Yes or no? Should we do something like this again? Yes or no? Would you attend? Are you interested in future Alliance events? That kind of information is going to be very important to us. I would like to announce that the next forum that we're going to have with the Texas Alliance will feature nano manufacturing technologies. And I think this thing, from my perspective, this event went pretty smoothly, at least from